So like I was saying, it's really fun to do application questions with these. The tangent ones, not as fun. It's like, kind of like, they're cool graphs, they're different, they have asymptotes, and I mean, they're still interesting to graph, but we have found if we were to give you guys more time to study for the final, we want to cut tangents off. I think I only get 1.5 days to actually study for the final. So when May comes, I'm actually going to post practice exams and practice sample quizzes, I guess, and I'm also going to give you a pack that you guys can chip away at. Okay. But with that being said, I love the applications. I think they're kind of fun today. So we're going to first start off really easy with like graphing or writing an equation in a model. Because once you guys have a model, you can make predictions. In fact, we're going to end with me giving you some hints for this last question, numbers 11, 12, and 13. When you guys have a model to go off of, then you can say, oh, what's my prediction for this time of day? Or what's my prediction for this? The things that are periodic. So kind of fun to see these. But let's just start really basic. Could you guys look at a graph and could you guys come up with the equation? So that's the skill we're going backwards and kind of coming up with what the A is and what the different parts are. Okay? So let's come over here and hurry and just make note of any details. What are some details from this graph? I'm sorry about my crappy drawing. That should have been better, but it is good. So pretend it's good. Okay, go ahead.
I would say the max and the min are 3 and -3, so that's just 3.
All right, so we go as high as 3 and we go as low as 3. So that tells us what about our midline? -3. What does that tell us about our midline?
Straight 0.
It didn't move, right? So it's a lot like the parent function. So what does that tell me as far as my equation goes? I'm not going to have what part? I'm not going to have anything plus or minus from it, right? Okay, good. So since I go as high as 3 and -3, my amplitude is 3. Perfect. And that goes in front. Okay, what else can you recognize from this graph?
It's a sine.
Why do you know it's a sine for sure?
It starts at the midline.
Good. At 0, we notice it's at the midline. So on your guys' homework, we made it not so easy. Like we have it look like it's just a continuous graph. So you guys can kind of zero in on, where it is at 0. And it's not going to be as easy as just like giving you just this perfect one period here. Okay, perfect. So you have that as the sine function. And there always has to be an x. There always has to be an independent variable. So next we need to calculate what our b is. Now, this one's actually really straightforward because what does it look like my period is?
Does it move? I don't see.
Your period is 2 pi over b typically, right? And our period on this one is 2 pi. So that means it's just a 1, right? So we don't really do anything, it's just sine of x. So this one was actually a little too easy, but I do you see how we kind of built it and how we kind of just we went backwards, we normally look at the amplitude and then kind of start drawing the graph, and now you will build it backwards, okay? So let's do one. I wish I did a shift on this one, but we're going to do one from your homework that has a shift. This one doesn't have a shift, you can tell, but it does change period. So I do like this one because I want to kind of start kind of small. So let's kind of build our model. What do you guys notice this is? Is it a sine or cosine? It's a cosine, I just heard. Good. What else do you have? Is it positive or negative? Positive. Okay, good. What else?
It says instead of 2, it says pi over 4. So it changed.
Our period did change. Yep. So this is our period. Okay, which means that's going to affect our b, right? Okay, we're going to calculate that in a minute. Let's do something else that's the easy part. What else is pretty easy to recognize? What's easy to recognize here? What can go right here? Amplitude can you guys tell that my amplitude is just a 1/2, right? So my amplitude is kind of front and down, and I didn't shift anywhere vertically, yeah, so my midline stayed at 0. So we've got to calculate our b. So calculating a b is a calculation. You guys use the formula for period. So since period, the formula is typically 2 pi over b, you guys take this 2 pi over b and set it equal to what the period is, and then you guys get to calculate for b. So you have to calculate it, it's not as straightforward. So you don't get to just take pi force and put it there. That's a common mistake. This number was not the period, this number was a part of the formula, right? So we get to calculate what 2 pi over b equaling pi fourths is, because this is our period. Okay, so let's go ahead and calculate it. I like doing cross product, it's the easiest. 8 pi is equal to b pi, and then what do? Get b by itself. So I'm going to divide by pi. So what did we just notice our b is? 8. Now if you want to double check you actually calculated your b right, go back and take 2 pi over 8 and make sure that it matches what you had. Oops, that's right there. Make sure it matches what you have for the period. Does that sound good? We came up with a model, and that is the model for this one. Okay? So those ones would be pretty straightforward. I'm actually going to do them from your homework. So those of you who have that still on your desk, let's jump. I think I liked number 6 because it has a different period. It also has a shift. So if you guys don't mind, we're going to kind of jump to your homework for a second, but it closed down on me, so I got to hurry up with it. Right there. Okay. So let's look at, it's not gonna let me just scroll through here. Let's scroll this way. Yeah, number 6 it is. Gosh, why doesn't it let me scroll? It's obnoxious. Okay, 1 second. It's not. It's just, no, it's on PDF. Is why, and I don't know why it doesn't like the. It doesn't like my like it doesn't let me just grab it and move it. Does that make sense?
Yeah.
It kind of is stupid. Okay, we'll just do this. It's not letting me do much. Okay. Okay, let's go ahead and do it. So the different things that we want to notice on this one is, first off, I like to use my max and my min to use that to figure out where my midline is. So one way you can figure out midline, give me a way you guys can figure out the middle of something. Like the straight middle. Okay.
I just look in like in between the periods.
Look in between what?
The periods. So like
Look
there's
in.
a half period, like the pi 6, and then the period
Okay.
before it,
So yeah.
where it like crosses the x-axis with like.
Okay. So are you trying to use like this shape and
Yeah.
seeing where it's like crossing?
Mhm.
Okay. So you're like imagining, so you just are more visualizing it, is that correct?
Yeah.
Perfect. Visualizing it is perfect. If you can do a good job of visualizing it and counting and making sure that this is equal to this, then that's great. That's one way too. You can also go up here and be like, oh, my max is at 1. My min is at -3. You can also find the middle of that max and min by taking the average of it. So that will help you guys find your midline. -2 over 2 is -1. So this will help you guys find where your midline is, if you want to just take the average of 2 numbers. Okay? So let's go ahead and start here. I have a lot going on, but if you guys want to go from one point to the next, that will help us state one period. Okay? So first off, based on me marking this off and saying, all right, here's one period, let's go off of this. So I'm gonna mark in blue the one period we're going off of, and I want from here for you guys to tell me how to build my model. What can we start filling in?
First, we can tell it's a negative coast.
You recognize that it's below the midline, so you're recognizing it's a negative cosine. What else can you recognize? I know this is zoomed in, so just disregard those smaller numbers, by the way. But what's our amplitude? 2. Very good. I don't know my b yet, so just kind of put x for now. But we also recognize the midline. Anthony recognized it was where? -1. Okay, so we're almost there. We just haven't calculated the b. Okay, how are you guys going to calculate the b on this one? What's my period? Pi thirds. So I get to say my period, pi thirds, is equal to this formula. Does that make sense? Since p equals 2 pi thirds, you replace p with the pi thirds. Does that make sense? Okay. So in case people aren't kind of like processing that, let me kind of re-emphasize that one more time. Do I have an eraser? I think this is an eraser. Yeah, this is an eraser. Crappy eraser. So remember, your p equals 2 pi thirds. That's the formula. You guys get to replace your P with what the period is and then calculate for B. Okay? Let's do the cross product. Did you guys get 6 pi is equal to B pi? And did you guys divide by pi? And did you guys get your B to be 6? Good. If you did it right. And there is your model. So that one was nice because we had a lot going on. We had shifts, we had a weird period, we had it be negative. It was a good one. Do you guys feel like you are pretty good if I move on to our applied problems? Okay, let's do it. So let me kind of get to the whole gist of why we want to build a model. We want you guys to be able to come up with a real life scenario, and you guys are going to kind of sketch a graph and to model what's going on, and then from that model, the second step in this process is to be able to write an equation. Now, I had students throw out a scenario to me, and so my students one year, I can't remember what year it was, like maybe 2 years ago, they're the ones that gave me these numbers, so I know these numbers aren't realistic, but they're kind of fun I like to kind of build problems from students, and it's kind of fun. You're also going to notice some of our real world examples are all in quadrant 1, because it's rare unless you're going below sea level that we're going to be going, because usually periodic themes have to do with time, like one of them is a pendulum swinging, one of them is like a spring that bounces up and down, up and down, up and down, like the spring isn't going through the ground. So you'll notice a lot of things are up in quadrant 1 because it's hard to go below the surface, like it's hard to go below 0. It's also hard, we don't go negative time. So you'll notice most of your stuff is here, okay? All right, someone else's voice. Does anybody mind just reading the scenario? I know this is a little bit ridiculous because we're talking about perfect world, and the number of seconds is a little bit long, but will you guys, someone read it to me?
I took my glasses off, I can't see.
Oh, come on. Micah, will you do me a favor and read it?
Yeah.
No, wait, yeah. Okay, go ahead.
Remember it?
Just this one. I'm going to show this one right here.
The group wants to create a roller coaster that is a continuous series of identical hills that are 20 meters high from the ground. The platform to get on the ride will be on the top of the first hill. They want to get 5 seconds for the roller coaster to reach the bottom of the hill, which will be 3 meters off the ground.
Thank you. Sorry, I can't see from distances, so I always get nervous, but I should have zoomed in on that. Thanks for reading. So I know 5 seconds is a little ridiculous, but we can still build a model off of it. And you guys, this is baseline building models. So everything in the mathematics world, we usually have a best fit. So even though a sine wave or cosine wave won't work for forever, it works for a portion of time. That's how these work. There's stuff that's like, oh, this is exponential, but it only works for a specific amount of time. Engineers who are dealing with like something that a projectile motion that shoots off, even though things work as a model, they're sometimes not perfect, right? Because we have different elements that kind of change the way stuff goes, but we can use models to make predictions, okay? So even though this will only work for a few, because not like the roller coasters are going to do this for forever, I can still predict where Anthony is, and obviously where you're sitting is also going to change things, but in a perfect world, one cart, we can predict where they are, how high they are to the ground 5 seconds into the ride, or 7 seconds into the ride. Does that make sense once you have a model? Okay? All right, let's do it. So I know this is kind of dumb, but we're going to pretend that we are getting on right here at time equals 0, and that's when the ride just starts. Because I know in a perfect world, we'd be able to just go. But like normally we like go up, and then like the way things work, you have to use gravity, But we're just going to go with it. Okay? So we're getting on the ride, and we're saying that the ride goes down and reaches a minimum, but then we have to go back up and it continues, right? And we're saying that they're identical, okay? Now, we only really need to worry about one period worth, so we're going to worry about from here to here. And so you guys, when you sketch your scenarios, are only going to worry about one period, even though this is technically going to happen for a few hills. Give me some information I can fill in on this graph. I also want you to label this y-axis and this x-axis. So give me anything from what Micah read. Go ahead, Ty.
It says that the top is 20 meters and it's going to be off the ground by 3.
Good. So this right here, we obviously don't like run into the ground, right? So this is the height in meters that you are at any given time, right? And then what should go along the x-axis because of what we said? Time in what?
Second.
Good. We're going to call this time in seconds. So what did Micah read? Do you remember what you can reread it or say it? We reached what? Bottom in 5 seconds. That's a pretty slow roller coaster, I guess. So that means in a perfect world, what should this be? This should be 10. So that's in a perfect, then our period is what? Our period is 10. That's not our B though. That's just 10. All right, so in order for us to come up with our model, we've got to use this. Okay? So I want my model in terms of x. And x is going to stand for, or t, we could call it t. If you want, we can just call it x because that's what we're used to. We need to decide what type of function it is, where is the midline, whatever. So here's our max, here's our min. You guys can find the midline a couple of different ways. You can use the average like I taught you. You could also figure out what the, because don't we want to cut this directly in half to decide where the midline is? So you guys can also figure out what this halfway is. Give me the different methods you guys want to try.
We can do the equation where it's like 20 minus 3, I think. And then
You want to minus them?
Or plus or whatever. How do you do it?
Well, you can do the average, which will give you the midline, but if you do the minus, then that's you figuring out the difference from here to here, which is great too. Which way do you guys like? Let's do the average. If you guys want to do the average and do 20 plus 3 and cut it in half, that will give you the midline. What is that? 23 over 2 would be about 11.5.
Yeah.
So that will give you the midline. You could have also done what? What's this difference between 20 and 3 here? It's 17. So if you cut 17 in half, then what is that?
Is it 11.5?
No, 17 in half? It's 8.5. That means this length, when cut in half, is 8.5 from here up, and it's also 8.5 from here down. So that's why that ended up being 11.5, because it's 3 meters off the ground plus the 8.5 amplitude. So you got to use proper reasoning and arithmetic when you guys are calculating the midline, okay? You can either, like I said, find an average and I'll give you the midline, but then from there you got to realize what this amplitude would be still. Or you can take the difference up here and cut it in half and then just make sure you know where the midline is. But from this information, we're almost there. We don't quite have our B. Now, my period formula, 2 pi over B, is going to be set equal to what? Nope, what was our period? 10. So now you get to solve for B. Now there's no pi's on this one, and that's okay. That means your B will have a pi. And that's okay. So let's go ahead and do the cross product. So 2 pi will be equal to 10b. And then I'm going to divide by 10. Divide by 10. So what do you guys notice my b ends up being? 2 divided out of the 10, and I'm left with what? Pi fifths. So don't be scared when the b happens to have a pi still. It's just how these more complicated ones. Especially when we give you whole numbers as your period. These ones will probably have pi still involved. Okay, let's build our model. Okay, first off, is this a sine or a cosine? Is it positive or is it negative?
Cosine.
This one is a positive cosine. Good. What else do we know? What would be my amplitude again? 8.5. Good. What goes inside with my b? What goes inside with my x? What's my b? Pi fifths. So you guys can say pi fifths x. And then what am I missing?
Plus 11.
Then I have a midline shift of 11.5. And there's our model. So from an engineering standpoint, I could say, where will this person be at any given number of seconds, right? So I could say, where are they going to be at 3 seconds? I could plug in a 3. But I would have to have this be in radians. That's my thing on numbers 11, 12, and 13. These are in radians, so you've got to kind of shift your calculator to radians because we're not using degrees, so we're using radians. So I could say, hey, where are we at 3 seconds? Where am I into the right at 7 seconds? Like now that I have a model, you could figure out how high someone's off the ground at any given second into the right. Obviously only for this series of hills. But, and then once we switch from not doing hills, then that's over. But, does that make sense how this works? How you guys can come up with a drawing and put together your model? Let me give you some hints for the future ones, and then I think we're going to be good. I'm not going to do any more from your homework. We took this one out, but this one represents how high someone is off of, so this one's a wave pool. We've taken this one out of your homework, but imagine I'm sitting in the wave pool, and then like I hear the buzzer, and this one actually has a horizontal shift because we took off this one because of the horizontal shift, but the wave pool buzzes, and then about 1 second into the ride, I feel the first wave come. How many of you have been to Lane Circle Swim? You pretty much just stay in place, right? And then you're like this far off the ground, the bottom of the pool, and then you're like this far off the bottom of the pool, and then you're the top of the wave, and then you're the bottom of the wave, and it's periodic, right? And so one period would be like, oh, top of the wave to the bottom of the wave, back to the top of the wave. How long did that take me? And you come up with a model, okay? That's an example of something that's periodic. This specific one, I'm not going to really do for you, but it's the exact same scenario. However, we started 1 second into the ride, and whatever, okay? Some people argue that if it is the same, I had students argue in the past, well, why isn't this a sine wave? Why isn't there at time equals 0, I started here, and then we went up, and then down? I'm like, that means it would have to take the same amount of time to get to this peak as it is to get back to your middle, as it is to get to the bottom. So sine waves, I sometimes run into us not using as many sine waves because it's kind of hard to have sine wave. Like, it's hard to go below and above a midline. But this is one that maybe we could finagle a scenario that would be a sine wave. But I'm going to go ahead and skip over this one since this one has a horizontal shift and we kind of run away with that. We do have one that is I'm going to try and get a hint on this one. Not on this one, but on this page. There is a pendulum one. There's a clock one that kind of deals with kind of the same idea as the wave one a little bit. You know how like there's a clock and it kind of rocks back and forth, back and forth, back and forth? Does that make sense? And so it's talking about how high this pendulum is here versus to here versus to here. So going from here down and back up is kind of like your the periodic being. So from here, like if I'm like 12 inches to 6 inches to 12 inches or whatever it is, okay? And so your job is to kind of draw, I think it starts, I'm going to make you guys kind of come up with it on your own, but it says a pendulum reverent is swinging back and forth at its highest point. Like, it's hard because we aren't really doing like a horizontal shift, so you could say your highest point is the start. Just make sure the way you guys drew your picture that your equation matches the way you set it up. Does that make sense to everybody? So even though the pendulum just stays, it's still like 36 inches this many inches, 36 inches this many inches, 36 inches this many inches, okay? All right, there is one that has to do with time sometimes. I want to know how you guys would handle this. Imagine something is mounted to a spring. And if gravity wasn't involved, a spring, if we were to like pull it and if it were to bounce back and forth, it would continue going for forever, right? But because we have gravity, it slows down eventually. So eventually a sine wave isn't perfect because it kind of gets smaller and smaller. But for the first few, you can use a sine wave, okay? So what it's saying is a spring is set in motion above a motion detector. Have you guys ever, in my physics classes, we had motion detectors. We did these experiments. And for my math major, we had to do in physics classes and my work. And people engineers who create the cool stuff that we use have to know how stuff works. And so there's these motion detectors. These motion detectors can judge how high that spring is up and down. So they can tell you at any time during the experiment where your block is. So if I stretch a spring, it's low. And then I let go, and the spring goes up, it's at a high, and then it comes back down, and then it's back up, it's back down. And for the first few times, we're hoping that you can kind of have a good estimate. Now, here is what the thing measured at 0.1 seconds, 0.2 seconds, 0.3 seconds, and it has this. Are you noticing how at 0.1 seconds it was down, or sorry, closer to the ground, went up, oh, it's coming back down, oh, it's going back up. Do you see that? So this is the data that this motion detector pushed out to you. So I told you guys some things are just best fit lines. They're not perfect for forever. So this one is, a sine wave is like a best fit line. So the way you would handle this is it's almost like you guys get to create like a scattered plot of what happened, you know, so like at 0.1 seconds, and you get to sit here and like kind of create a scattered plot, and then you would come up with your model. Now, we didn't make you guys do a scattered plot, so I would have loved to have done this, but the model, so it's called a sinusoidal wave. This one was a sinusoidal wave because we started at 0 and we stretch, and then it kind of goes back up. So this is a good example of one that can go like below and above the midline. The midline is where it is at rest, and then the stretch is the amplitude, and supposing in a perfect world, it's the same above and below, okay? And so that's why sinusoidal waves is a good model to use this one. So, anyway, and then we had you graph it. But your guys' specific example, just so I can get you working, is actually the time of year and the temperature. It's kind of the same idea. You know, and I think so you don't have to do a horizontal shift. You guys can consider time equals 0, like January. But you guys can be like, oh, the temp's here. But then in February, or month 1 or whatever, February, and so forth, you guys can sit there and you would create kind of like almost like the wave. And by the time you get back to December, you're probably back down to having your temperature be low again, right? And so our temperatures and our seasons here in Utah, at least, have very much a periodic type resemblance. It's not perfect, and it's the same every year, right? So this could be like an average over like the years. Like, well, this year it was here in January, but a different year. And so maybe you would have a scattered plot, but it's still, you can have like a best fit scenario. Does that make sense to everybody?
Middle of it.
Yep. So you're still going to come up with your max and min. You guys are going to still come up with your midline, and you guys are going to still come up, just call your period 12, for all I care, because it's 12 months. And you guys are going, and then once you have a model, I could say, hey, in month 5, let's estimate what the temperature would be. Does that make sense? And so that's how your guys' homework is going to work. So I'm going to be done. Oh, no, I have a hint. I'm going to be done in 1 more minute. Sorry. Let me give you 1 more hint to move on in your homework. And it's not letting me insert. There we go. Okay, here's a blank slide for you guys. Let me go through one more thing. Will you guys look at numbers 11 through 13? Whoops. And I don't want you guys to be scared off by this really daunting model. I want you guys to analyze it with me. I'm not going to answer any questions on there because I want you to have to do it. But I want you guys to analyze this with me, the different parts of this. We even have a horizontal shift, but I think because of our experience with transformations, you'll be fine. If you guys step back and I say, hey, this represents a thermostat reading. The data that came back, here's a sinusoidal wave that we came up with, that we noticed that this specific office building or whatever it is, has this as the temperature throughout the day. This is in Celsius throughout the day. And so we could always predict what the temperature with this model is at like 4 a.m. or whatever. So starting a day at 12 a.m. or 12:01 a.m., starting a day there. If I were to be like, what's the temperature at 5 a.m.? This represents the temperature, and this represents the time of day. So I'd plug in a 5. But what's the difference if I were to say to you, well, what's the temperature at 7 p.m.? Do I get to plug in a 7? No, because a 7 would be 7 a.m. So what do you do when it's a 24-hour period?
Oh, don't you use military time?
You use military time, yes. So 7 p.m. is how many hours into your day? Well, because it's 7 a.m. and 7, so you just add what to it? 12 to it. So it's how many hours into your day? 19, right? So if I wanted 7 p.m., I'd plug in a 19. So be careful about reading instructions, okay? The next thing is for us to be able to talk about like maxes and mins, and for us to be able to ask you different questions, we would want you guys to be able to, so another question is a max and min. So can you guys tell me which portion of this is your amplitude, which portion is the midline, like which numbers are your different things on your, if we were to graph it? We're not even asking you to graph this, but it helps you know the max and min and the temperatures and stuff.
Isn't it 60A?
Yep, this is our amplitude.
And then you have the change, like the
We're used to it being written here, but what's this? This is our midline shift, because this is our up and our down, right? So we're moving up 19. So now I know my midline and I know my amplitude. Do I know my max and my min temp throughout the day? I do. Pretty easy, right? So the last one that requires work is, it says, at what time X does the office reach its max? So once you guys know your max, it actually asks for now what time. So they actually want you to solve for X for when, I'm gonna make you do the work, when my temp max is at its max. Okay? So for instance, what's its max? What's the max temp in this room? This is in Celsius. My midline was at 19. So I'm gonna reach 25 at some point. So you guys get to put your 25 right here and solve for X and tell me what time of day that is. Now my hint to you is if it's above 12, then that's in the PMs. So you guys are gonna kind of like either talk in military time or tell me what PM time that's gonna be. But your job is to solve for X by getting everything moved away from the sine, use sine inverse, and use all your skills we learned last unit. So I'm gonna make you guys try that yourself, okay? But you guys will plug in a 25 and then solve for X on number 13. Does that sound good if I make you guys try that one on your own? Okay. You guys are off